I'm sure it was one of the easier, I'm sure once they thought it was technically doable, once they thought there was a good chance they could actually pull it off, that it was one of the easier things to do. Maybe I should turn this on now.
Just press it and hold it for a second. Oh, you're good. You're blinking green.
We can debate what the relative priority is, but the combination obviously was
It's the same result.
same result, unbeatable.
Good afternoon, everyone, and welcome to our weekly Thursday afternoon energy symposium. I have completely forgot who's coming next week, so I'm not going to tell you who's coming next week. It's Maria next week? Oh, it's our energy journalism fellow. I'm sorry. Thank you, Michael. I knew you were here for a reason. Maria Gallucci is going to be here next week. She's our energy journalism fellow at the Energy Institute, and she'll be talking about some of her research, which is focused on cleaning up maritime transportation fuels. One of the dirtiest fuel sectors we still have in the world is shipping. They primarily use what's called bunker fuel, which is an extremely low grade of petroleum fuel product, very polluting, especially in port environments where the engines are operating at very low RPM and very low efficiency. You get a lot of pollution. So she's looking into ways that are going on in the technology world right now, trying to clean up that industry with higher grade and cleaner fuels. This afternoon, we're pleased to have Dr. Charles Forsberg with us from Massachusetts Institute of Technology, MIT. I'm not going to read his bio because you all have it in front of you, or we forwarded it to you, and it's quite extensive. But let's just say, if you want to meet a guy who knows nuclear energy, this is the guy. He's been in the business his entire career. He got his undergraduate degree. Where did you get your undergraduate degree?
Minnesota.
Minnesota.
Yes.
Goodness.
Chemical engineering.
The cold part of the world.
Yes.
And he's been with MIT just most of your career,
No,
except for the time
I've
you're
been
in the
10 years.
national labs.
It's my retirement job. I was a corporate fellow at Oak Ridge National Lab, and before that, I worked for a company called SO Production Research, of which there may be 3 people in the world know that that's actually now called Exxon.
Exxon, yeah,
a minor little oil company that has a couple of minor facilities in this neighborhood.
Good. Well, this afternoon, Dr. Forsberg is going to talk to us about a way perhaps to make nuclear power plants a little more efficient, a little more viable, or perhaps a lot more efficient and a lot more viable by using some of their excess heat capability to put into storage and be a way basically to make a nuclear power plant more efficient and in a way rampable and load following and load leveling. So we've got about 45 minutes for his presentation and then time for questions afterwards. So, Doctor.
Okay. Oh, thank you very much. I'm going to talk about heat storage rather than electricity storage, which of course is the in thing. Sounds like a very primitive technology, some of it is, but it has one redeeming feature, and that is it's cheap. So that's the general thesis. If you're going to have storage, it better be economic. Otherwise, you might as well go home and it's irrelevant. I'm going to cover a couple of things. The first one is the obvious, economics is central. Second, electricity markets are changing. And third, 3 heat storage strategies to provide dispatchable electricity with baseload reactor operations. That means the reactor operates at steady state. The reactor operators are bored. We like bored reactor operators. Turbine hall, things are a little more exciting. We like exciting turbine halls. And we're going to look at 3 things, how to get variable electricity to the grid with heat storage in a steam cycle. Second, setting a minimum price for electricity with the excess energy going to industry. And the third, a nuclear power plant that buys and sells electricity depending upon the instantaneous price of electricity. Now, I'm only going to have one slide on economics, and that is that economics matters. The important observation here is that energy is 8% of the GNP. Cannot afford to double the price of energy without serious impacts on human standards of living on a global sense. And thus, you have to be economic. That's the bottom line. You know, if something's 1% of the GNP, you can double it. Maybe a few complaints, but it's no problem. If it's 8% of the GNP, and you double it or triple it, this is really, really, really bad news. Well, let's take a look at electric markets. And they are a-changing. Let's take a little look of history here. First, important to note, there's been no change in energy policy for 300,000 years. The strategy is quite simple. Throw a little carbon on the fire. And I show our previous version of heat and light called the cooking fire and the modern version of the combined cycle natural gas turbine. What is interesting about these 2 technologies, what they're identical in terms of how you think about them is they're economic at part load. You can run them at half capacity and it doesn't cost you any money. And the reason why is that the campfire with its stones and the gas turbine are low capital cost systems. There's not a lot of money in it. The money and the labor is in collecting the fuel, be it wood or natural gas, and bringing it to the fire. So although these technologies look very different, economically they're identical. You can run them at half capacity and it doesn't cost you any money because there's no money there. It's transporting the fuel to the fire. That's our strategy for 300,000 years. Now, let's take a look at the low carbon options. Nuclear, wind, and solar are high capital cost, low operating cost technologies. And if they're going to be economic, you have to run them at full capacity. If you run them at half capacity, the energy costs twice as much. Fundamental change in economics, and the first change we've had in 300,000 years. So you can understand why this energy change to a low carbon world is so difficult. We changed all the rules. Now, let's take a look at electricity demand. This happens to be the yearly electricity demand in New England for 8,766 hours. The demand is the vertical scale. I will make the observation that adding nuclear energy did not change fossil fuel energy markets or policies. And what we see is the baseload market. Nuclear's here, and the top part, the variable part that was provided by fossil fuels. That's been the historical model of energy for the last 40 years in the United States. Now, the question is, if no fossil fuels because of concern of climate change, what replaces the variable electricity production? What's the replacement for the gas turbine? That is the question. Let's look at this from a different perspective. Okay. Let's take a look at what happens if we add solar. This is some data from California, and it shows the impact of large solar deployment on electricity rates. And the red line, this is the price of electricity, wholesale price of electricity, and this goes over one entire day. This happens to be for the second Sunday in April. The red line is in 2012, the electricity prices. That's red line. Sort of constant prices. Toward evening, the price went up because everybody turned on their light switches and was doing cooking. Now, California put in lots of subsidies. They added lots of solar. Well, what did that do to the electricity prices? Well, here we go. Before the sunset, the prices went up, and then the solar came on, and the prices collapsed to zero. Actually, they went below zero, and they still go below zero, negative price electricity, because they have excess electricity and they have a subsidy, and they only get paid the subsidy if they dump the electricity on the grid. And as soon as the sun goes down, the price of electricity shoots through the roof. That's what the addition of solar does. Now, I'll let you know a little secret here. Nobody can make money on a solar system where the revenue or the value of the product is zero. This is like in New England, getting the price of tomatoes. Everybody plants tomatoes in their backyard, and they all turn ripe in August. Guess what the price of tomatoes in August is in New England? Negative. People are giving them away to their neighbors. So we got a bit of a problem here. Of course, this problem is a two-part problem. When the sun goes down, you suddenly need a lot of power, so you have to buy expensive stuff to produce electricity. And what you can see here is that large-scale solar collapses the prices, that is its revenue, when you have high solar input. And that limits economic deployment to about 15% of total electricity production, if you have good solar conditions. You can play the subsidy game, but you can't do that on a full-scale economy. Well, that's what's the impact of wind. This happens to be western Iowa wind. Price of electricity, multi-day cycle with wind patterns. So we're looking at multi-day. And guess what? If you install a lot of wind, price goes down, goes below zero, close to zero. Install a lot of wind, revenue collapses, limiting deployment. Bit of a problem. Now, what this says is we need storage to match production with demand. But then the question is, what kind of storage? In this context, I will note there are two options, heat or electricity, or actually I should say work, for those of you who had Thermodynamics 101 or whatever the equivalent thermodynamics course is at UT here. In this context, there's a big difference between nuclear and PV and wind. Nuclear produces heat, that is converted to electricity, and so we have the option of storing heat. We also have the electricity option. Electricity, of course, if you start with electricity, you want to store it as electricity. That means batteries, pump storage, a variety of other technologies. Well, let's take a look at this difference between heat and electricity. The first observation we make is that heat storage is cheaper than electricity storage. There's recently a detailed study out of Nature Energy that estimated energy storage costs for 11 technologies at the terawatt scale and came out with a scary number of $340 per kilowatt hour, which essentially means you just tripled your electric bills on an all-renewable system. Factor of 2, factor of 3. Now, the DOE battery goal for just the battery pack, never mind all that electronics, is $150 a kilowatt hour, with a lot of people debating about whether that is a fairy tale. The DOE heat storage goal is $15 a kilowatt, and by the way, that's by 2020, except it may happen before 2020. So what we see is that heat storage tends to be 1 to 2 orders of magnitude less expensive. And that's what this story is about. Buying cheap storage rather than expensive storage. Recognizing cheap storage helps nuclear, helps wind, helps solar, helps everybody except the gas guys. So that's the game. Now, I'm going to discuss three separate areas. I'm going to start with light water reactors with heat storage. And that it means variable electricity to the grid. It's coupling a baseload reactors with steam cycles for heat storage. We had a workshop on this last June. If any of you want to have an interest in the workshop proceedings, just type in that very long address at the bottom and the report will come up as a PDF file and you can take it off the web. So and most of this came out of that particular study. Now, I'm going to cover this a little bit later, but there are 6 storage options that you can couple to a steam cycle. I'll go through the technical details a little bit later, but I want to discuss the more broad section. But there are 6 classes, slightly different, and we'll discuss that later. Now, the important observation here is that heat storage economics, in addition to absolute prices, are different than electricity storage economics. Now, if you look at most electricity storage options, I'm using pump storage as an example. Batteries have a similar feature, almost all of them are similar. The storage systems has 2 separately sized systems. Now in pump storage, the idea is when you have cheap electricity, you pump the water from the bottom of the hill to the top of the hill. And when you need extra electricity, the water goes through a hydroturbine on the way down the hill to produce the electricity you need. If you look at the economics of pump storage, there are 2 cost structures. The one is the cost of storage. In this case, it's that a reservoir on top of the hill. And that works out to $1 per kilowatt charge. The second feature is the cost of electricity input and output. In these systems, there's a turbine generator combination that can operate as a pump, a reversible turbine pump with a motor generator that is a fixed dollar cost per kilowatt electric throughput. 2 cost structure, storage and the input-output device. And most other electricity storage technologies have a similar cost structure. Heat storages are a little bit different. It has 3 separately sized subsystems. It has a system that takes the steam from the reactor and inputs it to the storage system, measured in dollars per kilowatt hour, and for most of these storage systems we're talking about, that is very close to 0. It's a really small number. There's a second cost, the cost of storage, dollars per kilowatt. It has a third storage, taking that heat to convert it to electricity, and that's one of the more costly things because you have something called a turbo generator. But it's a 3-component system, 3 different things that you size separately with 3 different cost structures. And if you take a look at a power plant, you have several options of how you can do this. Option A, storage system uses power plant turbine for peaking load. Steam goes to storage when prices are low. I'm not going to go through that schematic, by the way. Stored heat to LWR turbine systems for added electricity. But the important point to be noted in a light water reactor, a nuclear reactor, is that when we take that steam and put it back into the storage systems, we only have to incrementally increase the size of the turbo generator. We have the option of using the power plant's turbo generator, the expensive component of the storage system, and instead of buying a standalone system, we buy our nuclear reactor with a slightly larger turbine and a slightly larger generator. Why is that important? That incremental cost is less than half the cost of a standalone system. Factor of 2, factor of 3 reduction in the cost of the expensive component, which is that turbine hall. Factors of 2, factors of 3 are economically very important. There's one other feature. If we use the existing turbo generator, it's operating continuously all the time. So if we want to add more power, we can add more steam very quickly, and the power level will go up or go down very quickly. So by integrating storage into the steam cycle, we get a couple of things, of which the most important one is knocking down the capital cost. The second one is fast response. The option B, of course, the economics, of course, for existing plants with added storage suggest a power output that would go from 80 to 105%. And here's our curve again of our solar curve. When the price of electricity collapses, we take a lot of steam out in a hurry. We lower the power plant's production and we dump it into storage. So we may take out most of the energy going into the storage system over a period of maybe 8 hours or maybe 6 hours. But then we bleed it back into the power generating system over 16 or 18 hours. So we minimize the size of the turbo generator system, the expensive component, and thus minimize the cost of our overhead storage, total storage system. Now, fortuitously for us, pure luck, it turns out that the solar curve matches very well with a steam storage system hooked to a nuclear reactor, because the solar only provides a lot of heat for a limited period of time, and it's easy for us to get heat out of the reactor and into the storage system cheaply. On the other hand, we can put the power back into the grid over a long period of time, so we don't have to buy a lot of that expensive generator, expensive turbine. Makes sense. This is customizing your engineering to match the market. It's very important on storage systems you start with the market. It drives your engineering. It's the only way to make the system economic. Now, new plants, if you do the analysis, we think a new plant might have a power output from 30 to 125%, where 100% is base load. The other option is heat from storage to a standalone turbo generator. It gives you a complete set of design freedoms, but it may cost you a lot more money, and money is, of course, the concern that we have in heat storage.
But I would think this would be a preferred option with an existing plant.
No, it turns out most nuclear existing plants have 10 to 15% excess capacity in the turbo generator set, and it looks like in most of those plants we can backfit. We can't dump all of the heat out, but we could go from 100% power maybe down to 70 or 80% power, a partial storage solution. New plants, you have much more freedom, but it's a plant-by-plant specific question. And there are lots of reasons for that. It turns out the nuclear reactor was expensive and the turbine hall was cheaper, so they oversized the turbine hall to make sure that if they could get an uprate, we'd still have wouldn't have to do anything in the turbine hall. Well, let's take a look at what the storage options actually are, the technology that I've been talking about. The first one is steam accumulators. You have a big tank of cold water, and what you do is you add steam to the cold water to create hot pressurized water. And so you got hot pressurized water, and of course what you do then is to get your steam out is you release the valve, open the valve, and you flash the hot water to steam, and the steam goes out to your turbine or your feed water train. And the reason you store hot water is it takes less than a third of the volume of your storing steam. What's the status of this technology? Let us show you the status of the finest technology built by Siemens in 1929 in their steam accumulator in Berlin. Charged, by the way, with a coal-fired power plant, 50 megawatts, mega-sized turbine, operated until about 10 years ago for a peaking unit. So that's the current status. That's the 1929 status. There's an accumulator at a solar plant in South Africa that is now coming online. You can see what the newest version of a steam accumulator is looking like, and it turned out in their case they optimized it to a bunch of horizontal tanks. I don't know if that's progress or not, but this is the 2017 version of it. So we can safely say this is a technology where the only question is which supplier provides the technology. It's really called off the shelf. Probably Amagoa would like to actually sell you the system if they could. A second option is store heat as a low pressure liquid or solid. This is done at a lot of solar thermal plants. The solar thermal guys, unlike the PV guys, have recognized that heat storage is a lot cheaper than electricity storage. And so most of the big utility solar thermal plants come with heat storage. They have come to the conclusion that selling electricity at $0 per megawatt at noon is a really bad economic model. And while the PV guys don't have any choice, the solar thermal guys are going to collect their production tax credit and not sell electricity in the middle of the day. They have an allergy to low income. This happens to be a Nevada one, which is obviously in Nevada. For reasons I haven't figured out, the actual oil storage reservoir is this curved, heavy section of pipe. I don't quite know why they use that as a storage system. It's obvious. There must have been something going on that I'm not aware of. But this is oil storage. They're using oil storage because this particular solar collector has oil going through it. So hot oil into this big set of tanks and into the little steam plant to the right. Westinghouse is currently looking at sensible storage for a nuclear reactor, and they have an oil-based system. Each module, and here's a module two modules on a flatbed truck, would store a megawatt hour of electricity. The modules are carbon steel. The thing about these carbon steel storage tanks is you get the steam creates hot oil. The hot oil goes to the storage tank and back hot oil to steam to feed water heaters. The thing about this is they discovered the most expensive component in the whole system was the heat transfer oil. Seems a little strange, but it turned out that was the expensive component. So their solution is these modules will be filled with concrete plates that are about 3 inches thick that occupy 95% of the steel boxes because concrete is cheaper than heat transfer oil. I know that sounds rather strange when you compare heat transfer oil to concrete, but concrete really is a lot cheaper. The round-trip efficiency for their economically optimized system is about 60%. That is, if you produced a kilowatt hour of electricity going straight to the turbine, you would produce 0.6 kilowatt hours going through the heat storage system. That could be raised to about 0.8 or 0.9, but the plant they were looking at, the economic optimum, came out from the design features at about 60% round-trip efficiency. The next one is cryogenic air storage. You take excess air and electricity, you take air and electricity and you make liquid air stored in a big tank. For peak power, you compress the liquid air up to 3,000, 4,000, 5,000, 6,000 psi. You vaporize it and you heat it. You first heat it up with cooling water, then you heat it up with high temperature steam. You run the hot air to a gas turbine, producing electricity, and you dump the air to the atmosphere, producing peak power. This is being developed in Great Britain. That happens to be the pilot plant. It's a 5 megawatt, 15 megawatt hour commercial demo plant in Manchester. And that particular plant happens to be integrated with a biogas power plant. Same steam conditions as a nuclear plant. So that's the status of that technology. Now, with that having said, we are going to go to technologies that are not as well developed. These three are deployable within a decade or less, some of them within 5 years or less. There's something called countercurrent Pebble-Bed heat storage. You input high temperature heat, high temperature steam, you heat pebbles, you get condensing steam, you get hot water, cold water during the charge cycle. In the reverse direction, for discharge, you push cold water in, you get warm water, boiled water, and steam. I'm not going to go through the details of that particular technology, but thermodynamically it should have the highest round-trip efficiency because it's a counter-current system. Lots of detailed, complicated work. It's in the laboratory status. Fifth technology is hot air storage. What you do here is you have steam and you have hot air, you have cold air, you heat the hot air. You may heat it again with electric heat. You take the hot air and you heat a pile of crushed rock to high temperatures and circulate back. To get your heat out, you reverse the direction of flow. The hot air goes through a heat exchanger, creating steam that goes to the power plant. The feature of this particular technology that is of relevant interest is the very low incremental cost of heat storage. That is, the cost of crushed rock approximately 3 inches in diameter. This is measured in $1, $2 a kilowatt hour range or less versus 350, 450, 550 for batteries. That rock pile, by the way, would be about 100 feet high. It's not exactly a small rock pile. But the incremental cost is very, very low. And the last option, of course, is nuclear geothermal heating, where you heat hot water. You heat a chunk of rock underground, typically 300-400 meters on a side, and create your own private geothermal heat source. Then you use a geothermal heat plant to get the energy back out as electricity. This particular option has the unique feature that seasonal storage is very straightforward, so you can just go right through it from A through Z. But it's very early in the development stage, lots of geology questions, lots of engineering questions. With that, I'd like to change subjects. Now that we've covered LWRs, that's the near term, and discuss the issue of, well, I've already covered that, the issue of Firebrick resistance heated energy storage, our second area. Now, as I mentioned earlier, when you put solar or wind on the system, you get a lot of zero-priced electricity. This technology is designed to set a minimum price of electricity by sending excess electricity from the electric sector into the industrial sector. What is it? Buy electricity when prices are less than fossil fuels used by industry, that is particularly natural gas. We have a lot of electricity in the U.S. that's sold for less of the price of natural gas. So if it's sold for less than the price of natural gas, why isn't it replacing natural gas? What we do is electrically heat insulated masses of firebrick to very high temperatures, and we use that stored heat delivered as hot air to provide industrial heat or peak electricity production. Schematic is shown here. Firebrick, you know, the stuff in the back of your fireplace. We heat it electrically when the price is low. When we need hot air, we blow cold air through the hot firebrick to produce hot air, adjust the temperature, for an industrial kiln or furnace. A partial substitute for natural gas. Now, what fires does is it buys electricity when the prices are less than the competing fossil fuel for the industrial world. So here we have our curve. If you install fires, it's going to set a minimum price that is substantially below the wholesale price of electricity sometimes in California or the wholesale price in Iowa. So it's a bottom dweller. We grab all cheap electricity and send it to our industrial colleagues. And the reason why this happens to be an energy diagram, I think most of you have seen it. That's the energy size of the electric sector. If you look at trying to dump a lot of excess energy somewhere, the only people who need a lot of heat all the time, 24 hours, 7 days a week, is the industrial sector. And so the answer is, if you've got cheap excess electricity, dump it to the only customer who's always there. You know, it's just a market-driven reality. Who can always buy if the price is right? State of the art, the Chinese actually use a version of this for heating large apartment complexes. This shows some modular units. Each of these modular units contain firebrick. They have a peak temperature of about 800 C. Input power level is 1 megawatt. The heat storage is at 8 megawatt hours. They use the hot air here to produce 85 C hot water for heating large apartment complexes. Now, I should explain what's going on here in China. This is because of a subsidized electric rate at night. If you go to China, you probably heard that they had a small little air pollution problem. Last time I was in Shanghai, I couldn't see across the street. It's not a good situation. A lot of that air pollution is local. It's generated by apartment complexes burning coal in boilers next to the apartment complex. Which creates really, with 50-foot stacks. This is not a good environment. And so the Chinese are trying to clean up some of their towns by providing a discount electric rate, electricity at night when available, stored in heat to provide hot water. Not a very efficient system, but it certainly solves the problem of local air pollution. But that's where the status of the technology is. Now, once you've developed fires, you have some other options. In particular, you can combine it with a gas turbine to buy or sell electricity, where we combine electricity generation and storage. Electricity generation either by natural gas or nuclear if we want a low carbon option. Well, let's take a look at our typical combined cycle plant. We take air, we run it through a compressor, we add natural gas, gets very hot, runs through a turbine. We turn the steam, producing more electricity, we take the steam, the heat recovery generator, steam generator produces steam, produces more electricity. If you think about fires, we have the option, if we have low-priced electricity, is to heat up hot Firebrick, run the compressed air, heated compressed air through fires as a replacement for natural gas, and run the gas turbine using fires heat. So fires is a way to grab cheap electricity, put it into a storage system to use later to run the gas turbine. Now understand, when the price of electricity is really low, the gas turbine is normally in the off condition. Nobody's going to run a gas turbine when the price of electricity is zero. Even at $3 a million BTU, it costs money. So this is a way to take that cheap electricity, store it, and run it for a gas turbine at other times. The strategy is very simple. Buy when it's cheap, store the heat, run the gas turbine when the price is high. Round-trip efficiency of electricity to heat to electricity is about 60% with a state-of-the-art gas turbine. Not great, but not bad. Now, the economics, there's a few technology development issues which I won't go into. You can ask me later. That's why this is not being done today, although I think in 10 years it'll happen. If you think about the grid as a whole, what do you require? You require storage plus generating capacity to prevent blackouts. Storage by itself doesn't solve a problem. If you have storage hooked with solar, what happens if you have a week full of cloudy skies and you have no solar? All of your batteries run dry, they're dead. What do you do for electricity? Well, you turn off the lights. Or in Texas, you might turn off the air conditioning. Now that would cause a revolution in the summer. Let's get serious. Light failures are one thing, air conditioning failures are far more serious. So if you think about the grid as a whole, you need storage plus generating capacity. And what this option here, what this option here does with fires and natural gas is we have the storage option, but we have the capacity in the gas turbine. Your alternative is to go buy an electric battery, pick any option you like, and then go buy the gas turbine when you can't generate enough, when you don't have enough storage in your battery to guarantee electricity. And our position is, this is going to look a whole lot cheaper than A plus B. Remember, in both cases, we're buying the gas turbine. That's the part that's guaranteed. So our goal is to make Firebrick cheaper than batteries. Again, all consequence of the change in markets. 5 years ago, there was no cheap electricity, and this would have been insane just because of the change in markets. Well, let's turn to the last subject. Well, we can take a high-temperature reactor, hook it to a combined cycle, and couple that to fires, and buy and sell electricity. That, however, is a slightly different game. It's zero carbon, and we have higher electricity to heat to electricity efficiency than any other system on the planet Earth. Well, let's take a look at the system. What we're talking about is high temperature reactor, hooked a gas turbine to produce variable electricity and steam. That's the game. A nuclear Air-Brayton power cycle. And the heat source for the gas turbine is nuclear heat, fire's heat, natural gas, or ultimately hydrogen. The good news is our gas turbine doesn't care how you get the heat. It's the beautiful thing about gas turbines, non-fussy on the fuel supply. It turns out if you're a nuclear engineer, you need to match temperature conditions. And this kind of power cycle will work with a FHR, that is a fluoride-salt-cooled reactor, solid fuel and clean salt. It'll work with a molten salt reactor. If you're an optimist and a physicist, it'll work with a salt-cooled fusion machine. Do we have any physicists or fusion guys in the audience? Or did I miss the wrong audience here? And it'll also work with a solar thermal power tower. Anybody who can deliver heat in the 600 to 700 C range, it'll work with. And the reason you have to be in the 600 to 700 degree range is that with a gas turbine, the first step is compress the gas. And the temperature of that compressed gas coming out of the turbine is over 400 Celsius. So if you're going to add heat to a gas turbine, you've got to be a lot warmer than 400 Celsius. You know, the gas turbine's driving this design. Well, let's take a look at the cycle with natural gas. We filter our air. We compress it. We have compressed air. It goes through a heat exchanger, getting nuclear heat. Heat from the nuclear reactor, heated up to 670 to 700 C, goes through a turbine, goes through a second heat exchanger, heated up to 670 Celsius, goes through the second turbine. Then it goes to the heat recovery steam generator, producing steam and more electricity, and up the stack. Now, the important point here is you've got the second heat exchanger, where the compressed gas is coming out at about 670 Celsius. That temperature limit is determined by the materials of construction of a heat exchanger. It turns out, in the real world, it's very hard to build an affordable heat exchanger over 700 C. Expensive materials. So heat exchangers tend to be limited to about 600, 700 C peak. That's what limits the exit temperature coming out of this heat exchanger going to the gas turbine. With this cycle, the cycle efficiency is around 42, 43, 44%. Not bad, but nothing very exciting. Well, the heat exchanger is limiting the temperatures to about 700 C here. But the gas turbine views 700 C as a cold, frigid day. We have industrial gas turbines running at 1400 Celsius. Mitsubishi has a commercial turbine on the test stands running at 1600 Celsius. By the way, that's the melting point of iron. It's a hot turbine. The reason, of course, the turbine can survive this is the turbine blades are internally cooled. There's cold air rushing through the middle of the turbine blade to keep the turbine blade cooled, because if it's all 1600 degrees Celsius heat, the turbine blade would go chunk and break apart in a few seconds flat. So we have a 700 C here and a 1400 C machine here. So we have the option of adding natural gas or hydrogen or a heat source here to raise the temperature. Let's say from 700 C, or in our case, the example we used, we can raise it up to 1050 C, which is an F-series turbine, or we could raise it higher with a newer turbine, get additional electricity out of the second turbine. This additional heat is a thermodynamic topping cycle, and the funny thing about thermodynamic topping cycles is they're very, very efficient, as I'll show you in the next slide. Here's what we have. Baseload electricity, 100 megawatts, 42% efficiency. We add additional heat above the low temperature 670 C gas coming out of the nuclear heating cycle. So we have a low temperature cycle at 670 C. I know that's not normally your definition of low temperature. And we add an additional 142 megawatts. The incremental heat to natural gas efficiency is 66%. That is more efficient than any standalone gas turbine or any other heat engine on the planet Earth. And we've only raised the temperature up to 1065. If we put a Mitsubishi 1600 C turbine here, that's going to be over 75%. And so what we have is a machine where the incremental heat addition is with a remarkable efficiency converted into electricity. And economically what this means is this machine, on paper at least, with natural gas can beat a conventional natural gas plant. A nuclear plant can beat a conventional natural gas plant because in peaking mode, it's more efficient at using natural gas than the gas plant is. And he who uses, the only way you can beat natural gas is if you use it more efficiently than the competition. Now, that's of course talking about natural gas addition, but of course, if we have low-priced electricity, we can use fires, which is made of firebrick. Turns out the only materials in the world that can go to 1600 Celsius without melting is firebrick. How convenient. So we can electrically heat the firebrick and produce and store hot gases that are then used as a peaking cycle in our gas turbine.
Charles, in these peaking cycles with that higher elevated temperature, is that a problem to the heat recovery steam generator? Putting a higher heat into that steam generator?
Somewhat higher, but fortunately our friends at all of the major turbine manufacturers have actually solved that problem. One of the things people do not appreciate is the big refineries, the big chemical plants all use combined cycle plants, which burn a lot of trash gases. And those turbines are designed for run up and down like a yo-yo over a wide variety of temperature ranges. So there are turbines that are out there. They have a little bit higher maintenance costs, but the turbines are available and the heat recovery steam generators are available. And all made possible, by the way, between the $1 and $3 billion a year the world spends on advances in gas turbines. This technology would not have been viable 15 years ago because the gas turbines weren't good enough. It's only in the last 15 years that the technology of gas turbines makes this a credible option. And so our strategy, very straightforward, with the nuclear Air-Brayton cycle is buy when the price is low, and sell when the price is high. Or buy when you have an excess, sell when you have a need. In short, a power plant that incorporates both storage and generation, the natural gas version and the nuclear version. The natural gas version, of course, has CO2 emissions. The nuclear version does not. Enabled by fires, but also enabled by the advances in gas turbines. And I cannot overemphasize that. 15 years ago, you could not have played this game because the gas turbines literally were not good enough. It's only with the F-series turbines that they became good enough. For those of you who are not familiar with the gas turbine business, there's the A, B, C, D, E, F, G, and the first H turbine went online earlier this year. So guess what comes after H? Well, where does that lead us? The most important thing is that markets are changing. 5 years ago, this talk would have been pure nonsense. It would have been a waste of your time. It would have been a waste of my time. It would have been a completely, totally, absolutely irrelevant talk. It's the change in the market. Very important. Second, a low-carbon world requires dispatchable electricity. People do not want the lights to go off or the air conditioning to go off. That's just the reality. And nuclear energy can provide that dispatchable electricity. The second observation is heat storage is much cheaper than work storage for a whole set of fundamental reasons, and that creates incentive to use heat storage. In our case, we're looking at 3 classes of heat storage technologies with very different characteristics. Steam cycles with baseload nuclear reactors for variable electricity. Always some output, but variable. Fires to consume excess electricity, setting a minimum price for electricity roughly equal to that of fossil fuels, and sending the excess to industry as heat. Sets a minimum price, avoids negative priced electricity, which is suicidal for solar, wind, and very bad for nuclear. And last, the gas turbines with fires buys and sells electricity depending upon need and market. And that's the unique capability by combining a heat storage system with the power generator. With that, I'll stop, and if you have any questions, please let me know.
Thank you, Charles.
By the way, I think the slides are available to anybody. If you can't get it from somebody here, send me an email. I don't know if you're going to post it on a website or what.
We will, thank you. I appreciate you sharing all that with us. And appreciate you nailing the time within 15 seconds. That was pretty darn impressive. I'm going to take the first question out of the microphone, and then we'll pass it on to Michael. All this is made available by the fact of price arbitrage, and that price arbitrage has, as you've been presented, been introduced into the market by the fact that we have electricity with basically zero fuel cost.
Yes.
That depresses the market.
Yes.
So as soon as this scales any significant degree, though, you're recorrecting that very market and in a way destroying that price arbitrage by your simple existence. Have you run the analysis to what degree of this type of technology penetration can be accommodated before you collapse that arbitrage opportunity?
We have to a very limited degree, but nothing that I would call really credible. It's going to depend also very strongly where you are. Is wind, solar, or nuclear controlling the grid? One of the things that people don't appreciate is in a fossil fuel world where fossil fuels are so cheap to ship is that we have a relatively simple energy system that looks the same everywhere on the planet Earth, more or less. In a low-carbon world, because of the variability of wind and solar at different locations, those systems are going to look very different in Texas than in New England, than in parts of Europe. So we're going to a much more diverse system. We're not going to have single answers, and there won't be a single answer to the question you asked. It depends where you are.
Okay, great talk. Michael Weber, Mechanical Engineering at the Energy Institute. We don't talk about thermal storage enough, so I thought this is really excellent. A couple comments. I had the same question as Fred, which is, with our analysis here, we look at the Texas market a lot. The first person that comes in to do the arbitrage makes money, but the second person doesn't, and then
that's exactly right. The first guy is going to do well, the second is not going to do so well, and eventually you get to the point where you're not going to make any money on this.
Right, yeah, but there's still value from the storage from ancillary services, which there's another 3 to 5 ancillary service markets in Texas, another half dozen proposed, which is things like regulation up and regulation down, a fast frequency response, and all these other things. And this is where batteries actually have useful utility, which is very fast. And thermal storage, I wonder, is it too slow for those? So I'd love your comment on that. And then one other question or prod for comment is, in Texas, storing heat is easy to do because there's so much heat, but heat's not as desirable, except in the industrial sectors. We like to store cold. And we do that here at UT, actually. We've got several hours of thermal storage that's chilled water and that kind of thing. Is it possible to use the heat for absorption chilling or other things? Have you thought much about that for a cooling climate like ours where we don't want heat?
We've looked very limited at using fires coupled to absorption air conditioners as a heat source where you have natural gas or fires depending upon the price of electricity. In terms of energy ability to handle control frequency, if fires is operational, you can, of course, cut off the power to fires in a half a cycle. So if you're in a situation where fires is absorbing electricity, you can drop that load instantaneously. So it has a very good controllability in one direction, but not in two directions. The gas turbine options where you put it, we have these nuclear Air-Brayton cycles or conventional gas turbines with fires and natural gas auxiliary. That's a different game because in those games, especially the nuclear Air-Brayton cycle, you can bring up the power theoretically in 50 milliseconds because you have a hot turbine above the auto ignition point of natural gas, and it's just the flight time between the fuel injector and the first blade. So there's some things you can do in the nuclear game that will compete with batteries. It's a very different, that system when you look at it, it's just doesn't have the behavior of what you expect from a gas turbine.
Okay, I have a question here. So you talked about those retrofitting options for the existing baseload nuclear power plants. Would that give implication to the NRA? Do they have to approve those additions into the existing plants?
There's been, as you know, we had a workshop on light water reactors last June. And about 10 years ago, Fort Calhoun was having a serious consideration about selling steam to Cargill for about 25% of its steam, 20% of its steam output. They did a preliminary run-by of the NRC of diverting steam. And the NRC said, you know, we actually don't see there's any safety significance to this. It's only one data point, but it does not appear it will have a large impact or require much by the NRC. And that's mainly because the NRC assumes the turbine can blow up. So what are you doing in the turbine hall that's worse than losing the main steam lines and the turbine going crazy? Well, certainly we're a much smaller perturbation in terms of safety than the turbine falling apart. So
That's curious. Just last week I heard the exact same story with the exact opposite result, that basically NRC resistance killed that potential project.
no, it did not.
Did the project go forward?
No, but it did. That was not the reason, because we had the project manager, the Fort Calhoun project manager there.
What did kill the project then?
What killed the project is there was a concern about tritium transporting the steam to the Cargill plant that also produced foodstuffs. That's what killed it. It was a legal liability concern. They weren't concerned about health physics, but the problem was, what if they got sued, and would they lose no matter what?
Because of the risk of the tritium.
Of the tritium. But it had nothing to do with the NRC. The NRC, the project manager was in charge of all of the interactions with the NRC. He said the NRC is not a problem. Now that is only a couple of meetings, so you recognize it's a limited set, but his takeaway in his notes and the NRC notes said this is not an issue by the people who were at the meeting. Always important to get the people in the meeting what their point of view is. Any other questions?
Thank you for coming down. Excellent presentation. Welcome to Austin. So it seems quite reasonable technology and innovative. Where do you see the next prototypes where it can have more proof of concept? I mean, this is somewhat, I'm not going to say simple thermodynamics, but it seems very realizable. And so is it a huge cost to develop reasonable sized prototypes? Where you could...
Well, let me start looking at both LWR heat cycles, LWR cycles, steam cycles, and then looking at fires. Last June was the first workshop ever held on heat storage with LWRs. I got everybody on the planet Earth there, the French and the British and the Japanese, and Exelon, which was a co-sponsor. And got to remember, the market has only changed in the last 2 or 3 years that this has become an issue for the utilities. The utilities are not always looking 20 years ahead. They're looking a quarter by quarter ahead. And that's why we had the workshop, very bluntly put. And we do know 2 utilities are now scaling up engineering studies to look at this. And that's partly been driven by the market, and partly they came there and they heard, oh, I didn't realize the technologies were in this state of form. I didn't realize somebody had talked to the NRC. And what they got out of the meeting essentially was, oh, now I know everybody in the game. And that's not a problem, that's not a problem, that might be a problem. So they got a feel of the lay of the land, and the feel of the lay of the land is that 2 of the utilities, which I'm not allowed to disclose, have asked me not to disclose, are now running engineering and marketing studies. On fires, the simple version is in operation in China. We're working with the Chinese for larger scale deployment. We are also working with Exelon, it's a nuclear utility, well, they're a utility in everything actually, and an unnamed manufacturer to get that commercially up and running for industrial applications. Fires in both China and the U.S. is partially a regulatory issue and partially a technical issue. Do you get the electricity before the meter, after the meter? Is it treated like a battery? Is it treated like a heat load? The regulatory issues may be as complicated or more complicated than the technology. But that's going forward on multiple tracks. And so we expect something in the next couple of years. It is most likely to be deployed in western Iowa or certain parts of California. And that's based on market considerations. In western Iowa right now, the price of electricity half the time is less than the price of natural gas to industrial customers. That's the driver. And theoretically, the numbers on paper say they've got a 2-year payback, maybe a 1-year payback. Wait and see, we don't know. Until you actually go out and build the darn thing.
See, I could see California being a stronger case over the long term because part of their issue is they have rooftop solar that isn't controllable like utility scale is, and they have the duct curve. As soon as the PTC rolls off after 10 years
Yes.
with the wind in Iowa, then over the long term, some of the negative prices could go away with that.
Yes, but Iowa has 2 other features. It has low-cost electricity right now. It has one other feature. They have lots of biofuel plants. And our friends in California pay more for low-carbon biofuel where you didn't burn methane or natural gas in your biofuels plant. So the strategy here is I'm going to build fires for two reasons. First, I'm going to reduce my heating bill, and then I'm going to charge California 20% more for my ethanol. So, well, if somebody's going to give me a subsidy for low carbon ethanol, I'm, you know, the issue of the market, the issue isn't installing 1,000 gigawatt hours of fires. It's the first couple of markets, and the first couple of markets for any new technology is some market niche where something crazy is going on, where the economics are really favorable.
So they have big wind in Iowa and they have big corn. And
Yes.
big ethanol plants.
Yes, yes. And some chokers in California that pay extra for low carbon ethanol. I apologize for my cynicism.
Sorry, I have one more question. So what you have introduced here, to my understanding, is more like the supply side management. So how can we, profit the most from the utility side? How do you looking at the also management on the demand side? There's a lot of data centers, server farms that can be take off grid at moment's notice, and there's a lot of those smart meters now in the in average electricity users, and they're also trying from the demand side to smooth out the demand curve. And how do you just say those two approaches in the market, which one will fare better?
It'll depend upon where your market is, but one of the things to recognize about low carbon electricity is a lot of it shows up at the wrong hours when the consumer market can't handle it. And the industrial market doesn't care. It doesn't care if it gets cheap electricity at midnight or at 3 a.m. in the morning or in the middle of the day. And the advantage they have in that context is, in addition to economics of scale, is they're always there. They're always in the buy mode if the price is right. Now, this is strictly an issue. The second one, which is much more local, it depends where you are on the grid. There's some very large differences in wholesale prices depending upon where you are on the grid because of transmission constraints. And so there are going to be some guys who are sitting in the right places or the wrong places from the point of the utility. You say, cheap electricity in my neighborhood, how can I take advantage of it? Fires, and some of these fires in particular, is very much a plant-by-plant analysis. It's not a generic, we're going to sell it to everybody on the planet Earth. It's going to be a plant-by-plant game.
Well, thank you very much, Charles. Fascinating presentation.
So I need to do anything.